Greetings to everyone present. My name is Patrik Goldschmidt from CESNET ALE, and this presentation will cover defense against SYN flood attacks and their way of mitigation in network-based environment. So let's get to it. I will briefly talk about our company. We will discuss DDoS attacks, more particularly TCP SYN flood. And I will present you three techniques based on network mitigation, SYN authentication principle, and we will compare them and provide some results in the end. So, about us. CESNET is an association of Czech universities and the Czech Academy of Science. In Czech Republic, of course. We operate and develop electronic infrastructure for science, research, and education in various fields, such as computer networks, computational grids, data storage, and so on. And we are also active in research in topics such as hardware acceleration, network monitoring, cybersecurity, and so on. This is our network in Czech Republic with 100 gigabits links, connecting multiple universities together and other networking hubs in the country. Well, we started basically with passive monitoring. We developed our own specialized hardware for high-speed packet processing based on combo architecture, and we were contributor to the first hardware accelerating monitoring card running at 100 gigabits worldwide. Currently, we are using 200 gigabits technologies, and we are planning or we are developing 400 gigabits per second. With this passive monitoring, it was all sunshine and rainbows, of course, at first. But in 2016, we experienced a major DDoS attacks on one of our clients, which congested our network. And for this reason, we started to develop an active DDoS protection to combat these types of attacks. So this solution, this protection, is called DDoS Protector. And as I mentioned, it runs on accelerated FPGA cards, and we are using our own firmware and software daemon. The device is currently running on 100 gigabits and is connected to the CESNET backbone, so is already mitigating some traffic, already helping to cleanse the network from attacks. How does it work? We basically monitor the network, and when we detect that some DDoS may be present, we update our routing rules on the router to redirect some source prefixes to this DDoS protector device. The DDoS protector device will then apply its algorithms and get rid of the bad traffic. It should be that simple, but of course we know that the world is not deterministic in this way. Okay, we offer top-end sources policing feature, which is good for amplification attacks, and we also provide SYN flood mitigation heuristic techniques, which is this presentation practically. Okay, so I already talked about DDoS attacks. Just very briefly, I suppose you are familiar with the topic, but if not, DDoS attack is a cybersecurity attack with the goal to disrupt normal operation of the target. It is done by flooding, often malicious, but not necessarily malicious traffic. But the point is to flood the network or the target device in a high volume. So the network or the server cannot handle the large amounts of traffic, and the denial of service situation begins. According to Cisco, 14% is expected growth of these attacks per year. And the prognosis for 2023 is 15.4 millions of attacks per year, which means that the number will almost double. That's the prediction by Cisco. The second graph by Kaspersky shows us the distribution of these types of attacks. TCP SYN flat is the most popular one, as we are monitoring the field for several years now. TCP SYN flat is almost the first, so sometimes second, but it's very popular type of attack due to its simplicity. It is very efficient, and many networks or devices lack the protection to combat it. So we will be discussing this attack right now. As you probably know, transmission control protocol is with us for some time. It will be actually 40 years of this protocol in September. So it's quite an old guy on the internet. And when the protocol was designed, the authors just didn't think about possibilities of such attacks. The security was not so big, was not a big concern back then, we know. But the protocol is still a fundamental part of the internet, and it provides features such as reliability, which is the base of many applications we use today. And of course, the protocol is connection oriented, which means that the session needs to be established before the actual data transfer is made. This session establishment is made by TCP three-way handshake. This process is crucial for the SYN flat attack and also for our mitigation methods that we implemented. At first, the client sends a message with SYN flag set with some sequence number of X. The server responds by acknowledging the message. Acknowledge is X plus 1, and the sequence number of Y, plus setting its own SYN flag. So I want to synchronize the session. And the client responds with another ACK, which acknowledges the Y plus 1 of the server and increments its previous sequence number. So this process looks fine, let's say, but the attackers found a way to do a bad things with it. So TCP SYN flat, it is based on flooding a big number of SYN segments to the server. The server needs to allocate some small data structure for each SYN it receives. And also it sends a SYN ACK back so the session can be established. But the attacker will not respond with an acknowledgement segment, so the session is never established, and the data that are needed for the state information for each received SYN are just begin to take too much space in the computer. The network resources are exhausted, or the memory resources are exhausted, and when the regular user tries to connect to the server, then the backlog is full, it's not working, and the denial of service is here. So our goal in the mitigation is to drop messages from attackers and of course allow messages from legitimate users. So it's some sort of a classification problem or some labeling. We can look on that way. Mitigation techniques of SYN flat can be distinguished between three categories: on the protocol level, on the end host level, and on the network level. Protocol level include some TCP extensions like cookie transactions, TCP fast open, or usage of completely new protocol, something else than TCP, as SCTP. However, as we were analyzing traffic on our backbone network in April 2021, the TCP has the majority of share at almost 80%, UDP was almost 20%, and the SCTP is like this small number, so it's not really used. So the problem is still there, and the protocol extensions are not used because they require compatibility changes from software developers and hardware vendors and so on. So that's not the way, or it could be the way, but it's not used widely. And host mitigation techniques like SYN cookies, SYN catch, and random drop are efficient but sometimes we don't want to allow the malicious traffic to reach the end client. So we want to filter the malicious traffic on the network level, so the server's resources are not exhausted by processing the traffic. And so there are these network techniques such as SYN spoofing, EC spoofing. I briefly discussed them in our paper, so if you are interested, take a look. But we'll be mostly talking about SYN authentication techniques, which in my opinion are one of the best ways to mitigate the SYN flood attacks on the network level. Since statistical and machine learning require some baseline, require some data to train, and cannot react immediately because they need to collect some data first before they can do the classification. So SYN authentication techniques can be the way how to mitigate SYN floods. Okay, we will briefly discuss three techniques. The first technique, SYN Drop, is rather simple. We will place some firewall or some middle device between the client and the server, and basically limit the maximum number of SYN segments the client can send. Every client SYN segment is forwarded to our algorithm, and according to the chosen thresholds, there are soft thresholds and hard thresholds, the number of packets is allowed to pass to the server. Soft threshold is active when client has sent no acknowledgement. And the first SYN is always dropped. This is to prevent port scanning. The hard threshold, which is typically much bigger, let's say several hundreds per second of SYNs, is active when the client has sent at least one acknowledge. The rationale behind this mitigation method is that when a dummy attacker just floods the SYN segments to the network, he doesn't send any acknowledgement packets. So his traffic will be effectively policed to some maximum limit, which shouldn't be able to affect the server and cause the SYN flood scenario. Of course, when the attacker is smart enough and either injects some acknowledgement, can be random acknowledgement to the session, or use many spoofed IP addresses, then the method will not be able to effectively mitigate the attack. That's why we implemented TCP reset cookies. TCP reset cookies relies on the fact that is stated in TCP, and it specifies that if the connection is in any non-synchronized state, such as SYN sent in our case, and the incoming SYN segment acknowledges something not yet sent, a reset is sent, which means that if we manage to create such an algorithm which always acknowledges invalidly to the first SYN segment from the client, we should expect the client, if it is implemented properly, according to TCP standard, to send a reset with certain sequence number. Based on this sequence number, we can add the IP address of the client to the whitelist and then allow sending some number of SYNs until the hard threshold is reached. It's also several hundreds per several seconds time window of the client. So this approach is known for years, and it was not popular at first because Windows 97 clients were not supported or were not compliant to the TCP standards. According to our laboratory experiments, the modern operating systems such as Windows 7, 8, 10 are compatible with this RFC, of course Linux, macOS, and so on. But the Fedora-based Linuxes utilize the state firewall of NF tables. And this state firewall typically drops these packets which are destined for non-existing sessions before they reach the kernel. So the kernel cannot respond with the reset because the packet is dropped before. This is a problem which makes Fedora-based clients somewhat incompatible with this method. But it still can provide some level of security in a case that nothing else works. And the third method to combat the incompatibility with Fedora clients, we called it a TCP Handshaker, but it basically is very similar to TCP reset cookies, except that instead of invalid SYN we respond with valid SYN We establish a regular TCP three-way handshake, add the client to whitelist at the end of the session. Then we need to reset this session because the client thinks that it successfully established the session with server, which is not true because the server hasn't seen any data from the client yet. So we need to reset the session, and then the client can send some arbitrary number of SYN which are forwarded to the server up to some hard threshold again. So this is compatible method and is rather efficient to combat these attacks. I forgot to mention that TCP Handshaker and reset cookies are effective against spoofed IP addresses because we require some response from the client, and therefore spoofed IP addresses cannot be used because the attacker cannot possibly guess the right values to respond with. And to generate these values, to be able to authenticate the client, we need some system of generating these values. That's our number generator module, let's say, and we need to generate acknowledgements for SYN in reset cookies and sequence numbers in X for TCP Handshaker. There are two policies of generating these numbers. They can be random or they can be hashed. The random numbers are per time window, and the hash is per connection, in which we hash source IP secret, some secret ports and timestamp, create a 20-bit hash, and append 12 bits of timestamp to the end. So we can reconstruct these timestamps and be able to validate the client by calculating its hash. And we also support two security modes. The hashes or the numbers can be generated cryptographically secure or just some regular hash and regular pseudo-random number generator. Okay, so results and comparison. We are mostly curious about the impact of these methods on the client. As we found out, the initial delay is rather high because the TCP retransmission timer in operating systems sets almost 1 second when the session is reset or when the session is timeouted. The TCP stacks in operating systems typically wait up to 1 second to retransmit the lost TCP segments. So this is quite significant initially, but after the client is whitelisted, then the traffic is only forwarded and there is almost no delay, as we can see, 0.08 milliseconds for SYN Drop and 0.13 for reset cookies and TCP Handshaker. So the initial delay is rather high, but after the client gets to the whitelist for some time, of course, then the delay is not that significant. From the perspective of mitigation device, we need to discuss what is the throughput limitation of using these methods. When we use one thread and the software forwarding technique, so no mitigation is present, we can achieve of 30 mega packets, so 30 million packets per second. When we apply SYN Drop, the value halves almost to 17, 18 megapackets, and the reset cookies and TCP Handshaker various security modes, as I discussed, impact the traffic even further. Of course, the cryptographic hashing is the most hard to compute, let's say, so the impact on throughput is rather significant. However, when we run the methods on 8 threads, which process the traffic independently, we are able to reach the hardware limits of almost 100 megapackets per second. And this SYN Drop is slightly lower due to hardware limitations, but it should scale linearly in other hardware. Okay, and we also typically want to examine the behavior of these methods when the reset to SYN ratio is changing. There are basically two types of resets in TCP reset cookies, and resets can be matching or non-matching. When we are using the hashing technique, note that we use this timestamp as last 12 bits. When the reset matches these last 12 bits, we need to compute the hash for that. But when there is no match, we can just simply forward the packet because we know that the reset is not for our algorithm, but it belongs to some regular TCP communication. And with this in mind, we are able to optimize somehow the process. So when there are a lot of resets in the traffic, the hashing methods throughput slightly increase, and so on. When there are matching resets, so we need to compute hashing for every reset, the throughput slightly decreases. Something similar is with TCP Handshaker, but there are acknowledgements and not resets, but also they can be matching and non-matching. And when there is a lot of non-matching acknowledgements, the throughput is higher, and as the ratio is getting like one acknowledged to one SYN, the throughput decreases. Okay, so to sum it up, this presentation discussed SYN flood attacks. As we found out, the SYN flood is the most popular attack due to its simplicity, high impact, and lack of countermeasures. We discussed several mitigation techniques, and more precisely, we tried to mitigate the attack on the network level. We discussed three methods: SYN Drop, reset cookies, TCP Handshaker, which can be used on a live network to mitigate the attack. Each has some advantages and disadvantages. And the future of our research, well, the methods are already integrated, and we are basically waiting for real attacks to emerge to publish some fancy papers. For that, we can optimize the method, such as memory optimizations with Bloom filters. We can offload these algorithms to FPGA or use some machine learning to mitigate the attack. And with that, I would like to thank you for your attention, and goodbye.